Thank you. My name is Sanjeev, and I am joined by my colleagues Karthik and Bhavya from our Bangalore office. So today we are excited to showcase our comprehensive 5G wireless test tools. Yeah, I think most of you are well versed with GL, but for those who are not familiar, let me give a brief overview about our company. We are a 35-year-old company headquartered in Maryland, and we have our offshore development and support center in Bangalore, India, and we have another office in Shanghai, China. We also have several representative offices all across the globe. So you can reach out to us through any of these representatives, or you can always contact us directly as well if you have any of your requirements. We have many years of experience in the telecommunication industry, providing consultancy services and also comprehensive suite of testing solutions to verify network performance in various telecom networks, including wireless, fiber optic, and traditional landline networks. We work with many of the major telecom equipment vendors, service providers, defense contractors, and system integrators to meet their testing requirements arising at various stages of the product development life cycle. Our core strength lies in core protocol analysis and emulation across various networks. These products can interface to all the telecom networks, including wireless, fiber optic, and legacy networks. Sorry. These products can both monitor existing traffic flows as well as generate customizable traffic like voice, video, and data. It can be monitored, captured, and we can store, replayed, and emulated as the customer requires. Most of our products are PC based and they are quite like portable as well as rack based solutions. With this brief introduction, let me hand over to my colleague Karthik, who will dive into the key technology and other key aspects of today's webinar. Over to you, Karthik.
Okay, thanks, Sanjay. Here, I like you to walk you through how GL communication is helping engineers to simplify 5G standalone testing using advanced emulation, monitoring, and IP transport testing tools, what GL provides. So in these sessions, we'll break down the challenges in modern 5G standalone networks, understand how MAPS 5G emulation and our packet scan monitoring system and also packet export transport level testing tools work together to achieve end-to-end testing needs of customer, mainly service providers and telecom vendors. So before diving into the tool specifics, let's have a quick look at where the world stands with the 5G standalone deployment. So we'll be mainly talking about the standalone deployment, where most of the 5G core network is completely new, and it is applicable mainly for a standalone network. Okay, as shown in the figure, across the globe, the operators are shifting from 5G non-standalone, that was the initial massive deployment, to now a true 5G standalone architecture. Standalone is a foundation of real 5G capabilities to bring new features, which involves bringing ultra low level latency and different network slicing options and distributed user plane functions, and which completely implements real voice over new radio. According to reports, okay, the 5G is still in the phase of massive investment and deployment phase. So according to industry reports, 173 operators in 70 countries have already invested in public 5G standalone network, either through trials, planned deployments, or actually deployed. That accounts to around 27% of all operators of the entire world, which are actively investing in 5G, which are in a different phases of deployment. On the right hand side, at least 75 operators in 43 countries have already launched the public standalone networks. Okay, another 31 are actively doing the trials and expected to go online very soon. And 60 service providers are planning the deployment. Okay, so what we expect is we expect this momentum to continue for till the end of 25 and throughout 26 as well. Okay. It's also interesting to note on regional distributions. Okay. 7 out of top 10 countries with the highest 5G SA footprint is in Asia Pacific. China leads with massive 77%, and India follows with 51%, and Singapore at 37% level. So it doesn't mean that they don't have the coverage. It is a amount of traffic which is actually using a standalone core. Okay, so in comparisons, United States have a currently standards 24%. In Europe, the standalone network actual usage is much less, and it is expected to increase that share very soon. Okay, now let's talk about why standalone is much more complex to test than the previous generations. Okay, in 4G, most of the core functions were monolithic. Interfaces were fixed, and the architectures were relatively predictable. Okay, but 5G SA introduces a complete shift to a cloud native and service based architecture. Network functions now behave like a microservices. They exchange JSON messages over HTTP2. They rely on service discovery and dynamic load distributions. So new components like AMF, SMF, UPF, UDM, and AUSF and NSSF and PCF interact constantly across multiple interfaces. So this means telecom engineers must validate not just the individual procedures, but complex workflows and API level behaviors, timing of interactions, and multi-node coordinate under very high load. Testing is significantly harder compared to LTE, and a lot of testing need to be done. Okay, here, this is where GL maps and analysis tools can help. So as shown in the figure, maps allows you to emulate every major 5G core network functions. Okay, the concept here is simple. Instead of deploying full physical 5G core network in a lab, maps gives you very virtual, flexible, and script-driven 5G environment. Okay, so here you can test signaling, and you can test the mobility, and you can test the authentication and authorization, and PDU session management, slice selection, multi-interface workflows, okay, all without having a complete 5G network components. And also it gives engineer full control and repeatability of test, which is essential during initial development and also every new revisions of the software. Okay, for here, let me take some example to give how go into a little bit detail. Okay, let's take it look at AMF. Okay, so AMF handles registration, mobility, and connection management. In real network, it must support thousands of UEs attaching simultaneously. So how do you test before deployment? Okay, using maps, we can simulate mass registration storms. We can test mobility anchors. We can validate state transition, timers, retransmissions, and error handlings. This is incredibly important because AMF failures can cause a network-wide attach delays, and the user will be quite dissatisfied. So maps allows this to uncover these issues much earlier. When you look at the SMF, it manages the entire life cycle of PDU sessions. Okay, everything from session management to modification release goes through the SMF. It communicates with UPF using PFCP protocol on N4 interface. So your testing here includes PDU session establishment, correct PFCP message encoding and decoding, handling of errors and timeouts, and especially correct quality of service rule assignments. So it all depends on the subscription. The guarantee, like quality of service must be guaranteed for a given user. So maps can emulate every one of these scenarios, so making SMF validation highly controllable and highly repeatable. And another aspect is the UPF. UPF is not only it deals with the signaling, it also is an important node in 5G core. It sits on a user plane. It forwards the traffic between the RAN and data network. UPF must enforce a quality of service rules. Okay, it must handle millions of packets per second, and it must do with all these forwarding with extremely low latency and jitter. Maps, along with the other supporting tool like packet export and packet forge, helps to generate very high volume of GTP user plane traffic validate quality of service enforcement. That means like we could simulate multiple flows with a different rates so that we can validate low priority flows are compromised while high priority flows are taken care without any impairment. And also it measures the forwarding capability of UPF under stress. And also it tests various traffic load, different rates and packet sizes. And also it is important to generate various traffic patterns. Like since the user plane is supposed to handle all the traffic which mobile generates, there should be a way to generate a traffic which mimic all the usage of mobiles. For example, like video, file download is and social networking. So each and every application we should be able to generate, and we have tools which can do that. Okay, so what are the requirements for the 5G network? Okay, so first, first comes the protocol validation. That is the starting point. Engineers must validate NGAP and NAS and all service-based interfaces according to the latest 3GP releases. So it's not only done at once. Every new software release, these tests must be conducted. Along with that, this control plane, user plane procedures also must be done in terms of registration, PDU session management, quality of service flows, and network slicing, etc. So this can be done in two different ways. One is we start with wraparound testing. Okay, in wraparound testing, a single network function is a device under test. Okay, all of its neighboring interfaces are emulated by maps, and the DUT connects to the maps alone. Okay, the advantage of this approach is a fine control and also visibility into DUT's behavior. Okay, it's not like you are simulating like tens of node functions. Okay, here it concentrates on only one network function. It helps to identify protocol compliance issues and state machine errors within the TNF. Okay, here the main focus will be protocol conformance and negative testing that are easy to test and monitor. The next steps will be end-to-end testing. So here we are trying to test the entire 5G core network, often with our emulated RAN and UEs. On the other side, internet traffic generators. This approach checks all the network functions work together correctly in realistic scenarios. Okay, so end-to-end test could be like initial registration, PDU session establishment, and all the service requests. This one exactly mimic the live network traffic. That means it is like whatever could happen, like when thousands of mobiles connects to the network, same thing will be simulated in these scenarios. Okay, in practical, this wraparound testing and end-to-end testing is actually complementary. Engineers often begin with the wraparound testing, and they iron out all the network function issues in isolation. The next step is to progress to end-to-end scenarios to ensure everything works together. In fact, the robust test strategy is iterate between these two. First, you start with the network function isolation, go to the end-to-end testing. So if you find any issues with the end-to-end testing, then identify those issues and come and do the similar testing in the wraparound scenarios. Next one is the user plane. Apart from the control plane, user plane also is quite important because so the basic transport mechanism must be sound enough to make any 5G network successful. Okay, so accurate measurement of packet loss, latency, jitter, throughput, any duplication and reordering must be measured. And also at the application level, like voice quality metrics like Polka or objective voice quality metrics like R factors should be measured. Okay, so next one is, so apart from that, okay, these things have to be continuously repeated as the deployment is maturing. Okay, so there will be a lot of releases. So every release, the entire complete test case must be executed. So for that, we need automation and repeatability and the CI/CD integration. Okay, since script-based workflows, okay, also we support the Python and REST API, so it is easy to repeat the test case and automate this large amount of test cases without user intervention. And the main part is the realistic 5G network emulation. So it's not like simply generating a certain message content. Okay, so it should exactly emulate how and various scenarios and various mobile phones behavior should be emulated exactly. So this includes configuring RAN core, UE, and slicing behavior. Also real-time scenarios like roaming, overload, failure, and recovery procedures. So you could have what happens, a particular node goes and restarts. So those things also have to be measured. And also the product should be useful for the entire product cycle. Okay, so it starts from the development, integration, pre-deployment, and field trials, and also ongoing software revisions. Okay, so we have seen enough on emulation. Okay, so let's concentrate on the monitoring side. GL provides, along with the emulation, monitoring of 5G traffic. All the, except RF, we provide all the interfaces wherein it monitors traffic at every node, and it's able to collaborate those signaling messages and provide a uniformed CDR end-to-end call flows. It not only gives a control plane signaling, it also able to monitor user plane traffic like voice TCP flows for a given mobile, and it gives the elaborate statistics. So along with that, regarding voice, it goes much deeper to analyze what are the impairments that causes delay, jitter, packet loss, and duplicates and out of order packets, and measures both R factors and derive the objective quality of services. So in addition to this, can be used along with our intrusive voice quality testing, where we can measure using subjective quality of service measurements like PESC and Polka. Okay, so next one is, so here we just explain what MAPS is capable of doing. Okay, so with the GL Maps 5G emulation, we can emulate complete 5G network. As you see, this is a common framework where we have the same framework, which is enriched to support a wide range of protocols starting from TDM to 5G now. So here we can emulate gNBs and all 5G core nodes and UEs from the lab itself. So this let us bring up new interfaces quickly. Okay, inject both valid and invalid signaling and observe how the network will behave under control and repeatable conditions. So this will be very useful in R&D, where it's more focused on message flows and IE, things like that. Okay, so here MAPS doesn't just send the isolated messages. It creates a real-time protocol procedures and behavior streams across the entire 5G call flow. We can establish control plane sessions, set up user plane bearers, and drive real application traffic end-to-end. That means like we can verify everything from the registrations of PDA session setup all the way to real voice, video, and data flowing through the network, just like a live deployment. So next step is valid network node performance. Okay, using this environment, okay, so we can validate performance of any 5G node, whether it's a gNB, AMF, SMF, UPF, etc. And also we cover all IMS interfaces also. So it look at how fast the particular network function reacts and how it behaves under stress and fault conditions. This gives the QA teams a clear quantifiable KPIs before the node is moved to the production. Since it is a script-based, this one, it has a lot of advantage. This is driven by script-based automation, so engineers are not limited to manual and GUI-only operations. We can build reusable test scripts that encapsulates entire procedures from initial registration to the tear down of the sessions. With a single click, okay, the same test can be replayed across multiple builds, okay, multiple labs. So you can create a set of test cases which can be repeated during every build on across multiple labs and multiple customers. And it is highly customizable, okay, because it's a logic, the entire test logic is scripted. It's very easy to customize, modify, and automate complex test scenarios. If a customer asks for a special roaming flow or vendor-specific timing settings or new features from the latest 3G releases, we don't have to write the tool. We can simply expand our script. Okay, this flexibility greatly reduces the turnaround time, okay, when the new requirements arrive to us. Okay, these are some of the features. As I already explained, it supports both a control plane and user plane. So we also supply a small cell which supports where the real phones can be connected. Hundreds of phones can be connected. So it can make a call and it can browse and do various activities, and the users can see what is happening on each and every interface by monitoring using packet scan. Okay, and it also supports the TLS for all the service-based interfaces. So on the user plane side, especially on the voice, it can have a kind of speech to text conversions where we can test the IVS, voice recognition, things like that. And so on the capacity front, it can emulate hundreds of thousands of mobiles with voice traffic. And also it can emulate GDP traffic as at line rate like up to 100 Gbps. Okay, as I mentioned, like it could have a intrusive voice quality test measurements across the lab. Okay, using PESC and Polka. Since we support like a CLI interface, so Python APIs can be developed by, we provide a set of Python scripts and it can be expanded by the customers to suit their needs. Okay, so let's consider about one of the transport testing needs. Okay, 5G has to make sure that the entire IP backbone, either at the 5G core or it is a backhaul, midhaul, and fronthaul, is absolutely error-free before deployment. Okay, so we do have a product called Packet Expert, which has good traction, and it supports from 1 gig to 100 gig, 1 gig, 10, 25, 40, 50, and 100 gig line rates, and it verifies all like BERT, RSC2544, WIDOT 1564, and TCP throughput testing. So which measures what is the throughput performance counters, whether it has a latency, frame loss rate, and jitter. Okay, so along with that, it supports PTP time synchronization and also sync key verification. It is essential, maybe like just before the deployment or during deployment, we need to ensure that entire IP backbone is intact. Okay, so the other options we have is ability to simulate customers traffic, be it voice, video traffic, all the downloads, all the social networking, YouTube, those kind of services. Okay, Packet4G is a product along with maps which can be used once a session is created. Like we could generate like hundreds of thousands of mobiles. Okay, the control plane signaling once it is over, we will be able to generate user plane traffic which generates these behaviors. Like each mobile we can simulate to have one voice call. Simultaneously they can have a video streaming like YouTube. You can have a file download or some of the social networking traffic behaviors. So while doing everything, okay, for every session we will be measuring the latency, packet loss, and throughput performance matrices. And also we have a ability to playback pre-captured PCAP file across thousands of sessions in a stateful way. Okay, so the traffic rate need not be constant. We can have a burst or ramp up and down and random traffic rate over time. So those simulations also are possible. Sanjay. So now I'll hand over to Bhavya to continue details of emulation.
Yeah, thanks, Karthik, for introducing us to the 5G capabilities that GL offers. Yeah. So from this slide onwards, I'll be just discussing the practical use cases where you can use GL test tools and how you can actually connect a DUT into the environment. So very basic, the first use case currently I have not mentioned here because all the initial discussions went on the complete 5G emulation. So that complete 5G emulation will be useful in many cases. So majorly in testing any 5G monitoring tools available. So if the user is, if anybody is developing their 5G monitoring solutions, so they cannot always tap to your live network. So instead of that, if you have the complete emulated end-to-end 5G core, so that they can always tap in and test their monitoring solution. That is the major use case for an end-to-end 5G emulation. So along with that, that same end-to-end 5G emulation can be very useful in training the new engineers and also useful in the educational institutions. So to design any course or anything, so the complete visibility will be available without actually the 5G live network. From this slide, we are actually discussing different practical use cases where we can, as Karthik mentioned, the wraparound testing. So different wraparound testing combinations where we can make use of GL's emulators. The first one here, this slide actually shows a use case where MAPS gNB emulator is used to test entire 5G core network. So here MAPS gNB emulator actually emulating the N1 N2 interface, thereby emulating internal virtual UVs without the RF interface. So in this case, gNB can inject all the NGAP NAS signaling from the emulated gNodeB towards the 5G core. So it will be very hard if you want to load the 5G core with actual real UVs, because it may be very difficult to drive the real UVs. So in this case of emulated gNodeBs, where emulated gNodeB can emulate hundreds of gNodeBs and thousands of UVs, that were virtual UVs, which can inject N1 N2 signaling into the AMF. That includes the NAS, NGAP signaling, and it can emulate, it can drive UV registrations, authentication requests, security mode, video session setups, and it can also have idle inactivity and release procedures can be emulated. And along also it can, with the help of packet here, emulate certain data browsing capability also to load the core network. As mentioned earlier, as MAPS is fully scriptable, so you can create positive and negative scenarios, invalid NAS messages, wrong timers, the out of order sequencing, so that you can test the invalid, you test the behavior of your 5G core. So in this case, we are using another flavor of the 5G emulator from GL. So in this case, we are considering one of the ORAN interface, that is the ORAN element, that is the distribution unit, as a DUT. So in this case, we are acting as gNodeB control unit that actually emulating the F1AP signaling. So this is one of the new introduction into our new addition to our GL protocol family. So the new ORAN interface. So here we can generate F1 control plane and the user plane signaling to test the DU. So actually DU is the one distributes the signaling received from various UVs to the 5G core. So that has to actually connects to the CU, that is the control unit, via FNAP interface. So then CU will be connecting it to the AMF using the N1 N2 signaling. So if anybody is developing the new DU, so instead of testing against the entire 5G core, they can opt for GL's FNAP emulator, where it can act as a control unit to test the complete DU functionality. So here also our gNB CU emulator, or the, what you can say, FNAP emulator, can manage all the UV context, transferring of the RRC messages, supporting bearer setup and management, even the data track. So it can terminate all the signaling happening from the DU and respond accordingly. This is another variant here. So currently in the previous slide, we were considering DU as the DUT. So in this case, we are considering gNB control unit as the DUT. So in order to, if you consider gNB control unit as the DUT, so you would require to test FNAP and FNAP functionality as well as the N1 N2 functionality of the controlling unit. So as gNB connects to AMF via N1 N2 signaling and to the distribution unit via FNAP signaling. So to test this, so we can act as we can use GL's emulation and the N1 N2 emulation. In the FNAP emulation, the distribution unit also emulates the internal virtual UVs to emulate all the FNAP propellant signaling towards the control unit. So upon receiving all the FNAP signaling, controlling unit will actually trigger N1 N2 messages towards the AMF. Here GL's N1 N2 emulator, acting as an AMF, can terminate all the signaling messages from the FNAP and responding accordingly. It can also maintain the context and the ciphering. It can take care of the ciphering and integrity protection. Okay, it can test registration, authentication, and all the signaling which is possible from the FNAP point of view as well as the N1 N2 point of view. So thereby testing the complete capability of the controlling unit. So in the first slide, we actually treated 5G core as the duty, and we used GL's gNB emulation. So in this case, if anybody is developing the gNB, actual gNB, so to test the gNB functionality, again, there is no need of the complete 5G core before actual deployment. So you can test against N1N2 emulation, where AMF can bring you the complete 5G core, virtual 5G core. So thereby terminating all the N1N2, that is NGAP as well as the NAS signaling. The same, all the functionality, all the signaling which can happen via N1N2 can be tested. So not only the mentioned here, PD session establishment or PD session management, context management, also SMS SMS over NAS also can be supported in this use case. Yes, this one is the classic example of the wraparound testing. So in this case, we are considering AMF as the duty. So we are wrapping AMF with all the emulated nodes which actually surrounds AMF. So this, as AMF is the heart of the 5G core network, so it has to connect to various 5G core elements using different interfaces. So namely N1, N2, N12, N8, N11, N20, N17, which are currently supported in our case. So here, apart from N1, N2, all the other interfaces which are present in the right-hand side are the service-based interfaces, meaning they are actually having they are HTTP-based messages which carry JSON JSON as the payload. So in order to test this AMF, we can use the GL's gNB emulator at one side to generate all the N1, N2 traffic, also hundreds of gNBs and thousands of UVs. And we can test the behavior of the AMF whenever different test cases are triggered here. So whether it contacts the actual AUSF or UDM or SMF, it has to contact AUSF for the authentication parameters retrieval, and then UDM for all the subscription data gathering, and SMF to create and manage the video sessions, and then SMSF to generate the SMS over NAS, and EA for the check IMI identity check request. So whether the AMF is handling all kind of these scenarios so that we can test with all the emulated nodes. So yeah, this can be done in a very repetitive way, and we can also test the behavior of the AMF by triggering invalid messages, or we can also test timeout conditions, etc. Yeah, this one is an example of the UDM isolation. UDM is the complete, it's a database, for example, in 5G core. So this is the complete service-based interface. It doesn't interact with any of the other binary interfaces. So every interface is in service-based here. So here UDM can connect to different network functions such as AUSF, AMF, SMF, SMSF. Here also we can surround UDM with different emulators in order to test the complete UDM capability. So whether it can provide the requested information or not. So complete subscriber data management in various services will be tested in this case. Yeah, this one is the simplest simple isolation, that is the AUSF. So this can be tested using GL's N12 and N13 emulation, where in Intel N12 AMF will trigger the authentication request towards AUSF, and AUSF will contact for the authentication vectors recovery and creation of the authentication challenge keys. By wrapping around the AUSF, we can test whether AUSF is behaving properly or not, or whether it is giving the proper services or not. Yeah, the next example is the SMF isolation. So here, usually SMF will be present within the core where it connects to EMF and UDM and the UPF. So in this case also, we can test the complete behavior of the SMF by triggering the PDU session request via N11 interface. And we can check whether SMF can pick the different UPFs, and we can check whether SMF can transfer all the N11 requested parameters to the UPF, and whether the actual data flows are successfully established or not. Yeah, this is an example of the SMSF isolation. This one will help in testing the SMS over NAS case. So where EMF can generate SMS over NAS in N20 interface, and SMSF can retrieve the subscriber information from the UDM for the SMS subscription. And SMSF can forward the received MO SMS to the destination SMS via same AMF. So that can be tested using this variation, this combination. UPF isolation. So this one is the most interesting testing where we are considering UPF as the DUT and acting as the SMF. So here we can emulate all the signaling happening on the N4 interface, that SMF can trigger all the PFCP association signaling and can test whether UPF can handle all the PFCP associations. It can create the requested PDU sessions and modify the PDU sessions, and whether it can respond to multiple PDU session requests and IP address management requests, etc. from the SMF. So we can also make use of the packet forge in this case in SMF and the UPF to test the UPF capability, whether it can convert all the N3 traffic to N6 via, and we can validate using the packet forge. Yeah, this one, in this combination, we are testing the EIR capability by acting as an AMF by triggering all the identity check requests, whether it can give the IMA check requests, that is the IMA status responses properly or not. And finally, this one example is the NRF isolation. So in this case, the device under test is NRF. So we are wrapping NRF around all the 5G network functional elements. We can register different network functions, and we can check whether the requested registered network functions can be discovered by other network functions based on the specific criteria defined by the user. And we also support the subscription and the notification procedures here, along with the bootstrapping. So we can surround with multiple network functions in order to test whether NRF can discover all the network functions. So till this slide, we have discussed various use cases where our 5G can be used. So now I'm just introducing to the new web interface. Currently, we are introducing new web interface. Till now, the Maps application was supported on Windows, which was a limitation. So currently, we are introducing the web interface. So in the following slides, we can just see how these web interface is easy to configure different 5G, how easily the 5G core can be set up using our web interface. So from the browser itself, you can add the 5G elements. So here you can see, you can add the different kinds of 5G nodes. So you can select which one you want to add. You can add multiple nodes and multiple instances of them. And you can even configure every node, the transport of every node via browser. And you can start calls, stop calls, and you can watch the statistics. We can also monitor the health of all the nodes, whether they are in the connected state or any node is disconnected. So we can completely view every from the browser. So this is the testbed configuration where you can configure the transport of individual nodes along with the node properties such as the SST or SD information or the range of UEs it can support. So all the node information can be configured in the testbed. So once the nodes are configured and testbed is started, you can have a node connection status where you can see how many nodes are there and how many are active and how many are inactive. We also have the profile editor in the web interface where you can configure all the test parameters. For example, this one shows a UE emulation configuration. So where we are configuring the different SUPI values and TIMC, IMEI, and type of call which want to be emulated, and the authentication parameters. So everything can be configured via profile editor. It's a JSON file internally. So we also have the call reception windows here where you can place the call and see the call flow along with the message decodes. Similarly, we have load generation where you can select the load patterns you want to generate. You can select the script and the number of profiles, that is the UVs, and then hit start. So then it starts generating the load. So once it starts generating the load, you can look at the statistics for actual load generated, whether they have how many active, total, passed and failed calls, etc. In the node statistics, you can see the sent and received message statistics in each and every node separately. We also have events and error logs to keep track of the issues or anything for the debugging purposes. And we have a message editor similar to a Windows application. So here we can create variations in the NAS and NGAP message structure. So the next one is the YAML editor. So this is the 5G exclusive feature, that also web interface exclusive feature, where you can load the YAML files provided with the 3GPP specifications for the individual SBI interfaces, and you can see what are the messages available or the HTTP message and JSON contents, and you can easily create the messages from the YAML editor. Yeah, so till now we were looking at the emulation capabilities. So as Karthik discussed earlier, so we also have an 5G analysis where we can mirror all the 5G traffic to a switch, and using our packet scan, we can collect and all the signaling, and we can segregate the signaling messages into calls, and we can even decipher NAS and maintain security context. We can also monitor the complete IMS call and N1, N2, and PFCP. And if the SBI interfaces are available, so it can decipher NAS. So yeah, this is the packet scan decodes of the 5G. Yeah. So this is showing like how packet scan can monitor and show the end-to-end 5G call flow. So yeah, I think this is where we can conclude all the 5G testing capabilities what GL can offer. Yeah. Thanks, Sanjeev. That's over to you.
Yeah, thank you, Bhavya. Thank you, Karthik. Thank you once again for everyone for attending this webinar. You can always contact us by filling up the info request form, or you can send an email to us at info@gl.com. We'll be more than happy to answer your questions. Thank you once again.